Okay, so there was an announcement from the computer. The meeting is being recorded. Now I'm going to return the window to the full size like so. These are some of the hardships. If you do upgrade to 5.1, there are some hardships. Okay, now I received a question in the chat window. Let's address this question. Is there a class calendar with tentative dates for homework and reading? Okay, what we have here, there are a couple things available. So again, the document camera is one of the meeting participants. One more thing I should do is spotlight. I right click on the document camera, I spotlight it. I think that it serves to really do everything I can. I have, in the language of Zoom, I've pinned the document camera, and now I have spotlighted it. And not only that, I made it a co-host. Those are 3 different concepts in Zoom. So again, this is an overview of our summer session. It's an 8-week summer session. And I got a question in the chat window regarding the schedule. So I have some of the homework due dates solidified, but other due dates, we're going to tweak them a little bit. So I don't have a complete schedule right now for all the homework due dates. Earlier today, I published homework 1. So let me record that over here. So homework 1. Okay. Homework 1 is available on B Courses. It is due on Sunday. Okay, so homework 1 is due on Sunday, 11:45 p.m. Okay, the reason I do that is you'll see some instructors use 11:59 p.m. That serves only to introduce an extra element of madness and hysteria because it's 1 minute before midnight. Okay, there's no need for that. So let's have it be 11:45 p.m. This serves to mellow out the situation, so to speak, and yeah, there's no fundamental difference. So anyways, it'll be due 11:45. What's important here is that you take your homework, and we're asking that people do this handwritten. So handwritten homework. We can allow for a couple people to use LaTeX, but just a couple. If it turns into a problem, we will have to unilaterally outlaw LaTeX. So yeah, you take your work, you create a PDF file, and here's the thing. I personally advocate using software from trusted sources. So what I personally do, if I need to create a PDF file, I take some photos, and then I use, well, since I'm running Linux, it's natural for me to use the LibreOffice, something similar to Microsoft PowerPoint. And I simply put those photos into a deck of slides and I export as PDF. So that's what I do to create a PDF file. The important thing is you have a homework assignment, which is several pages, and then you create a single PDF file. Okay. Many students these days will use apps on their phone, and there are popular apps. So officially, I cannot endorse any of those apps because oftentimes these apps request access to all kinds of user information on your phone, which is actually not necessary to create a PDF file. So to make a long story short, if you have any questions about how to create a PDF file, contact us and we will help you. And again, our first big milestone here is Sunday, 11:45 p.m. PDF file. Okay, now there's another question in the chat window. Will you post the answers to the 7A final? Yes, absolutely. I will post the answers. And let me record that here, because I'm sketching out a bigger picture here. What we have is the so-called homework 0. Okay. As an abbreviation, I wrote HW0. That's homework 0. And you know it consists of 2 things. We have the 7A final exam. and then the actual homework 0 problems. Okay, and so what's happening here, you know that homework 0 is not to be submitted, okay? This was useful to us to go through the motions of a homework assignment, okay? So you should have been studying these problems intensively, especially this item here. This portion, right, there are two portions. There's a Physics 7A final, and then there's this portion here. This portion contains some problems out of Taylor. Let me fix the W here. It's bugging me. Trying to make a better W. Okay. In particular, we studied some things last time. It turns out if you have a conserved quantity, and we'll talk more in our meeting today, if you're studying one-dimensional motion, if you have a conserved quantity, then you can write down a formula for the time t as a function of position. And in principle, you have a solution. It's been reduced to the problem of an integral, okay? So this foundation knowledge, which is very important to us now in Physics 105, we exercise that knowledge here. Okay, so that's homework 0. And the question I got in the chat window, yes, I will be posting solutions here. And again, the usual cycle is 4 days. So approximately 4 days after this was originally posted, I will post solutions. So those solutions will be available pretty soon, within the next couple days. Now, homework 1, we're doing something special. And this is also an answer to the other question I received in the chat window. The details of the schedule of the homework due dates, okay? This particular one has a very special due date this Sunday. That's unusual. Ordinarily, our homework assignments will be due Tuesdays and Fridays. Always 11:45 p.m., typically Tuesdays and Fridays. That's the nature of having a 7-day week, and we're doing approximately a 4-day homework cycle. So you'll see these things due on Tuesdays and Fridays. So I'll publish some more details about these due dates. Part of the issue here is we need to talk about the exams. And in the syllabus, I indicated the dates. We have 2 midterm exams and we have a final exam. Thus far, it seems that students are okay with these dates. And if that's true, then we can really crystallize our schedule. We'll have great clarity about homework due dates, etc. Yeah, so we will have, coming soon, we'll have great clarity about homework due dates and the details of the schedule. Okay, so yeah, in summary, what we're gonna do today, we'll talk about some of the mathematical methods here. Homework 1, right? This is our first major item, right? Because this is homework that you actually do upload. All right, so let's talk about where we're going this week. Remember, the most important thing here throughout this summer session is that we must be in a fundamentally different mindset. During a regular semester, you have 15 or 16 weeks to cover all the material, right? During the summer session, we have 8 weeks, and we don't even have the Friday of the last week. Pretty much that last week, it ends on Thursday, and that's it. The party's over on Thursday, okay? And the administration really wants us to bring it to a close there on that last Thursday. So in summary, we have to work at a furious pace. We have to work twice as quickly. And it's challenging because you can talk to the various administrators in the physics department. Physics 105 is considered to be the most difficult physics course by physics majors. That's what they have concluded. I think part of it is we're going to introduce a lot of advanced mathematical methods. Now, you know, we're entering a new age where we're going to have Python programming. This means we're going to reduce the amount of advanced mathematical methods. Okay, so that could be a change here on the horizon. Because we cannot simply add more and more to the course. We cannot ask you to self-teach a semester's worth of Python and do Physics 105, etc. Okay, so today we're going to talk about mathematical methods that you're going to need for homework 1. These are methods that we're going to use throughout the course. Okay, so we'll be talking about these mathematical methods. So let's begin again with a triangle. I'm trying to draw a right triangle. You know, there's only one more thing I have to do is draw this vertical line. Okay, not too shabby there for the right triangle. Okay, and for a planar surface, of course, Pythagoras tells us c squared is equal to a squared plus b squared. Okay, now what's going to be important to us here in homework 1, and as we proceed through our course, we're going to oftentimes need to write an approximate formula. So the exact expression for the hypotenuse c, of course, the exact expression is that c is the square root. Okay, that's exactly true. Okay, well, if that's exactly true, why would we mess with it? It's already exactly true. What's the point of transforming it further? We're going to transform this further. The point is, we will often get a better understanding of a physics problem by introducing approximate results. So for example, if A is much smaller than B, what can we say? So consider okay, what if the ratio of A over B okay, and the important thing is notice this is a ratio. A is measured in meters, B is measured in meters, but this ratio, this is a pure number. Therefore, it's meaningful to say it's small. If somebody says small, that means you compare it to 1. That means 1.0. Okay, you compare it to 1. If it's much less than 1, then we have a small quantity. So what we can do in this case is we'll factor out the B. So this is the following. We have C okay. Oops, I went off the paper. Sorry about that. So you see what we've done here is we've begun a transformation. For homework 1, you're going to use skills similar to this. Notice what we've done is we've taken this expression here, it's exactly true. It's exactly true. There's been no approximation thus far. This expression for C, the original one, square root of A squared plus C, that's exactly true. And this one is also exactly true. Now we're going to use a certain theorem, and these are available. There are some interesting results on the inside front cover of the book. Okay, and this theorem that we're going to use is called the binomial theorem, also known as the binomial series. Okay, so actually I should rephrase that. The binomial theorem is usually used for finite terminating series. We're going to use the so-called binomial series. Okay, the binomial series, again, it's available if you open the cover of the textbook, look at the inside front cover, it's there at the bottom of the inside front cover. Let's write down this series, a wonderful series. We'll talk about the relationship to some really beautiful classical mathematics. You've probably heard of Pascal's triangle. It turns out that triangle should actually be attributed to a different researcher, Tartaglia. He discovered that earlier, but let's not worry about that. Let us proceed as follows. Notice we're using the variable lowercase z. This is customary if you're talking about complex numbers, and this is true for complex numbers. So we're going to see that this statement is true for complex numbers whose modulus is less than 1. Any complex number inside the unit circle in the complex plane, you have this wonderful result. We're going to raise this to the power n. Now here the notation is a little unfortunate. We often use n for integers. It turns out this theorem is true even if n is not an integer, and we'll talk about that some more. On the homework, we're going to have n being 2.5, 2.5, also known as 5/2. Okay, so here we go. This is equal to 1. The first correction there is n times z, and the next one really shows you where this is going. It is n times n minus 1. Okay, so there's the binomial series. Notice if this n is an integer, then this is going to terminate, right? Because the structure, what we've done here following the textbook, this term here really shows you the structure of what happens. Subsequent terms have the form n times n minus 1 times n minus 2 over a factorial. And of course, 2 factorial is equal to 2. This would be correct if we had written 2 rather than 2 factorial. But the reason the author left the 2 factorial there is to show us the pattern. And this now really is a very nice term in terms of illustrating the general pattern that emerges here. The cubic term would have n times n minus 1 times n minus 2 over 3 factorial times z cubed. Okay, so this is true if the modulus of z is less than 1. Okay, so there's the binomial series. What I'm going to do here, for clarity, I'll put a box. Okay, so again, this box, which I drew in pencil, really serves to clarify the situation that this binomial series is a very general result. Again, it's available on the inside front cover of the textbook. And it's true for complex numbers. In our example here with the triangle, we're completely happy with real numbers. A over b is a real number. In this picture, it's something like 0.6 maybe. The point is it's a pure number, and it's less than 1. That's all we ask. We want to talk about a pure number, which is less than 1. Okay, then we're justified. Let's get right to work here. We identify this as a product. This is b times the square root. Okay, that is to say we're going to have this little n be 1/2. Okay, let's get right to work here. We have a little n equaling 1/2. So this is now c. Okay, again, we have an overall multiplicative factor of b. And now the structure that emerges 1 plus a small quantity. Okay, notice the small quantity is a over b squared. That's okay. The entire thing, a over b in parentheses, and that thing is squared, that's going to play the role of z. So let's get right to work. We have the 1. We have n times z. So that's our 1/2. And our z, okay. So we've seen a couple things here. In the binomial series, this term is called the linear term because we have z to the first power. This is called the quadratic term because we have z to the second power. Now, what we did is we used the binomial series and we truncated after the linear term. So that's linear in z. But because our small quantity here is a over b squared, you see this 1/2 a over b squared. All right, so, and there's a dot, dot, dot to indicate that there are more terms. We have an equal sign here because it's understood that you want to write infinitely many terms. If I have the dot, 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 that indicates we have the infinite series. And if you sum all of those terms, then this is truly equal. If we truncate this, then we have an approximation. So C is approximately equal to B Okay, wonderful. And let's just rewrite this slightly. So we get C is approximately equal to B plus, and now we got the A squared over 2B. So you see, we did a little bit of cleanup. We had an a squared over b squared here. We had a multiplicative factor b. There you have it. So this is the first correction. So if a is small, let's look at our picture again. If a is small compared to b, then we can say that c is slightly longer than b. You see, that's what's emerging here in our formula. I see the document camera is a little bit not as big as it used to be with zoom 5.1. Okay, so c is slightly greater than b. And how much greater is it? Well, the answer is it's approximately a squared over 2b. Okay, so that's an interesting calculation. The point here is we took an exact expression, and on homework 1, right? These are motivational remarks. This is a little pep talk for homework 1. Homework 1 due Sunday. That's our first homework. Again, you have more than 4 days this time, right? Usually you should think of turning around these homework assignments in 4 days. But because we're just easing into the semester here, we're going to allow ourselves a couple extra days. That's why this is due Sunday. Okay. One of the problems on homework 1 is a problem where we examine the stability of a certain rigid object, the so-called super egg. And many decades ago, super eggs are very popular. They were mass-produced. People would have them sitting in their living rooms. I mean, they were all over the place. The super egg, and I provided a link there. There's a nice Wikipedia article about super eggs. So it's remarkable because it's an object that will balance. Like if you took an ordinary egg out of the refrigerator and attempted to balance it on one point, one of the endpoints, it's going to fall over. Not stable. But the super egg is stable. That's what we're doing here. We're going to bring in concepts of radius of curvature, right? And all of the things we've been talking about in terms of computing derivatives of functions and compositions of functions. Okay, so this little exercise here illustrates that, yes, at this point we had an exact expression. Then we did some subsequent transformations, right? So those are the milestones here. We have an exact expression. I'm pointing with the pen here. This exact expression for C, that was exact. Why would we do all this extra work to get an approximate? This is inferior because it's approximate. That was exact. That was perfection. Now this in some sense is inferior because it's approximate. Okay, but this is something we often do because we want to understand the difference between C and B, right? The difference between C and B, now we've got a much better understanding. If A over B is small, then this term here. In fact, I think we should celebrate with a little bit of colorful ink here. Yeah. Again, this is a red pen. If you don't believe me, look at that. The entire thing is red. Okay. I understand when I write on paper, it doesn't look so good anymore. That's been something that has been amply explained to me, but it's still kind of reddish. Okay, so yeah, this on the homework, on the last problem of homework 1, it's going to get a little bit messy, but just remember there are some guiding principles here. You can organize your results, and always, when in doubt, try and do this. Try and rewrite it so you have 1 plus a small quantity. In this example, we achieved that by factoring out a b squared inside of this square root. We factored that out, it became a b out front. Then we achieved our goal of having 1 plus a small quantity. Once you have that, you can use a binomial series. Okay, that's the key here. So what I've done for homework 1 is I did post a little bit of a hint. It's in the homework 1 folder. That's why we're using the folder structure. So you go to the homework 1 folder. There you will see homework 1 PDF. That's the actual problem set. But also I've included a diagram. Since I'm such a nice guy, I included a diagram to help out. And there's a good chance over the coming days we may provide some more helpful hints there. Remember, it's kind of a two-way dialogue. Chris, in section, you'll have some dialogue there. It's likely that we will provide some more guidance because the problem actually is a little bit intricate in terms of all the mathematical maneuvers you have to do. But remember, the super egg, these things were mass produced. They were all over the place. There's no question as to their ability to balance on their endpoints. So that's a fundamental topic here in mechanics. Equilibria and stability of equilibria, right? As we, again, the big picture for this first week, we're mainly focusing on chapter 5. At the same time, we're reviewing things that you covered in Physics 7A and Physics 5A. If you took those at UC Berkeley, then I know exactly what you covered. And that's going to be an issue here as we go through chapter 5 today. I know that a lot of that material is covered in 7A. Okay, those of you from other institutions, if you didn't cover this stuff, then of course we'll provide some references, and in discussion section we'll help to fill in the details. All right, so again, this week we are we're working as always twice as quickly as you would during a regular semester, a spring or a fall semester. We're going twice as fast. And so yeah, this week we're going to cover chapter 5. Now notice section 5.7, section 5.8, section 5.9. You can kind of skim through those. It's part of the reading assignment. You know, it's good to look at that stuff, but we simply don't have time to go into the details of those sections. So you will not see those on the homework or the exams. Okay, so soon enough, we're going to be in chapter 6. All right, so let's take stock of the big picture here. This week, we're going to mostly focus on chapter 5. We are, at the end of the week, going to go into chapter 6. And since we're going into chapter 6, chapter 6 contains some of the most difficult mathematics we're going to do. All right. This means we should take a moment to explain why we have to introduce the difficult mathematics. So let's do this. We're going to click on share screen. I'm going to show you a presentation that was done a few days ago by Andy Charman. Some of you probably know Andy Charman from courses that you've taken at UC Berkeley. He's taught a lot of courses at UC Berkeley. Okay, let's look at some slides that Andy Charman prepared a few days ago. And let's see what we got here. I'm going to click share. I'm going to click this thing. Okay, now again, I have to deal with Zoom 5.1. All right, so at this point, I hope you can see the slides. You see this was June 17th. This was a recent meeting, a collaboration meeting. I spent several years working at Lawrence Berkeley National Laboratory. I hope you can see the icon there. Again, for me, it's, I can tell you, you know, I hate to criticize Zoom 5.1, but they really mess up the screen resolution. And now I can see the LBL logo there, but it's partially eclipsed. I hope you can see that. Anyway, we got the University of California. As you know, Lawrence Berkeley National Laboratory is owned by the Department of Energy. It's managed by the University of California. There's a third generation synchrotron at Lawrence Berkeley National Laboratory, a user population, about 2,000 users a year ago there. Now look at the title here, it's in red. A simple variational principle for synchrotron radiation. So the point here is we're going to be talking about variational principles. We're going to be talking about the calculus of variations. Okay, chapter 6 in Taylor. This is where we introduce the calculus of variation. It's considered rather advanced mathematics. Okay, and so yeah, later this week we're going to go into chapter 6. So the reading assignment that we're currently working on is a good chunk of chapter 5. Tomorrow I'm going to announce the second reading assignment for this week, and that will be to finish chapter 5 and start into chapter 6. So at the end of the week, we're going to start doing some of this stuff from chapter 6. Let's have a quick look at slide 26. Yeah, look at that, slide 26. Look at that. Who's this co-author? It was a great honor to write this paper with these wonderful co-authors. These people are amazing, absolutely. And it was just I had several years there at Lawrence Berkeley National Laboratory working with these people. So this is FEL is a free electron laser. And so these are huge machines that produce radiation for scientific purposes. In this case, we're interested in X-ray radiation, soft X-rays. Okay, let me also mention, I'm going back, this was page 1 of the slides that Andy Charman presented. And you see on the second slide, this is in memory of Max Zolotarev. Okay, my office was right next to his, just a wonderful person. I was truly honored to spend several years, working on the same, we were on the 3rd floor of building 71B, and just a really great guy. So of course, it's very sad that he passed away. Okay, so again, I'm gonna click on this button here, and we're now back to our meeting the way it was before. That was just an example that the calculus of variations, very important, right? It's very important to us in formulations of classical mechanics. So this summer in Physics 105, we'll be talking about the calculus of variations. We'll see applications, okay? It's true that some of the material in this course can be done without Lagrangian mechanics, okay? You can do it just with good old force equals mass times acceleration. But some of the results, such as, when we get to chapter 11, if you have an arbitrary system and you're looking at oscillations about an equilibrium, the Lagrangian approach is just phenomenal. You can very easily solve the problem. So yeah, later this week, we're gonna go into chapter 6 and start the calculus of variations. Okay, so let me check the chat window. Here we go, we have a message in the chat window. The audio cut off exactly when you were mentioning. Okay, so the audio, let me ask you this. Can you hear me now? I think the audio's back. Can anyone hear me? Oh yeah, okay, great, thank you. Thank you for, okay, so one person did experience, okay, great. Thank you for that. Yeah, it's always nice to see the feedback there. Okay, so one person did have an audio problem, and so let me just repeat sections. I'll write it here. Okay. So just so we're clear on this, it was sections 5.7 through 5.9. Of course, this is really interesting stuff, but you see, we have to budget our time. And so some things we have to say, nope, it's not going to be on the homework or exams. So yeah, as part of the reading assignment, you should skim through to have a look at what's going on. It's interesting stuff, but, and it is useful to see how this, can be expressed in terms of our notation that we're using throughout chapter 5. So the idea is, as you read through chapter 5, you become very comfortable with the notation, and then it's useful to skim through these sections and see how the results look in the language of our chapter. Okay. So we're going to be solving differential equations. Let's make some general remarks here. Okay, so I need a new piece of paper. We're going to make some general remarks. Actually, I think I'm going to save us some time here. Let's do this. I think what we can do here, this is going to be a time saver. Yeah, ordinary, that's a good question. Ordinary ODE, that's an abbreviation for ordinary differential equations. And PDE, that's partial differential equations. We're going to be doing both. Yeah. So we'll start with ordinary differential equations. And here's what I'm going to do to save some time. Right. So the idea is we don't want to get PowerPoint overload. So typically I do write things by hand. But sometimes, a diagram like this, we can go through this. Let's look at the flow of logic. So for example, suppose you're looking at a simple harmonic oscillator. Okay. We write down Newton's second law. Force is equal to mass times acceleration. Okay. And for a simple harmonic oscillator, there's a restoring force which is proportional to the displacement away from equilibrium. Okay. If you write that down, the fact that the restoring force is proportional to, let's say x is your coordinate expressing your excursion away from equilibrium, you very rapidly get a differential equation. So that's this box here. And in answer to the question in the chat window, this is an ordinary differential equation. There are no partial derivatives. We have a function of a single variable. So we're looking at a function x as a function of t. X is a function of a single variable t, and we have derivatives just with respect to time. It's true that we have second order differentiation, but it's still an ordinary derivative, and it's expressed with a regular lowercase d. Now, there are two ways you can go. If you have a constant of motion, and in this case, the total energy is conserved, total mechanical energy is conserved, then you can go this route here. The total mechanical energy is conserved, and in one dimension, you remember we did this in our last meeting, we wrote down an integral for t as a function of x, okay? And then once you have that function, in principle, you invert it to get x as a function of t. So that's our goal in mechanics, to find x as a function of t. And again, this branch in the diagram was assuming you had some sort of constant of motion. If there's dissipation, right, and we will certainly consider a simple harmonic oscillator with dissipation, that's going to be a game changer for us, because then there's no constant of motion. The energy is not conserved. Mechanical energy is not conserved. Of course, the total energy, if you include heat as a form of energy, then yeah, that's conserved. But in terms of our differential equations, we don't have this nice linear combination of x squared and x dot squared, which is a constant. So here you must solve for x as a function of t. So in chapter 5, we're going to explore, this is kind of an overview. We have talked about this, and this is very important in homework 0, right? And we've identified material in chapter 4 where we use this procedure to get t as a function of x, right? We did this in our last meeting. We wrote a formula where t was an integral from x naught up to x of a certain quantity, right? And that quantity looked a little bit funny, right? It was certain dx prime over x dot. But we showed in our last meeting that it was fully rigorous. It's a very clear prescription how to get this function. Okay, so yeah, this is kind of the big picture for what we're doing in chapter 5. Now, when you have a simple harmonic oscillator with some dissipation, right? There's a little bit of friction, so you're losing mechanical energy. There are various special cases. There's the so-called underdamped case, the overdamped case, and the critically damped case. All right. For that stuff, we're going to appeal to your, if you took 7A or 5A, those courses covered those. Those are different cases here for these differential equations. So we won't be spending a lot of time in lecture on those different cases, but we do want to appreciate the big picture here. Okay, so we're going to talk about some methods for solving these differential equations. Okay. So here we go. All right, so for the simple harmonic oscillator, okay, simple harmonic motion. We very rapidly get to this nice differential equation. Okay, so you see what we have here is a simple harmonic oscillator. What's the motivation for calling it simple harmonic? There's just one frequency. Okay, so there are, in general, if you have nonlinearities, so when you take Physics 111A, you know, the electronics course, the part A, you'll have a lot of fun looking at various harmonics. If you have a nonlinear oscillator, then, and of course, many musical instruments have a very rich tonality because you get all these overtones. But for the simple harmonic oscillator, there's just one frequency. That's what we're going to see here. So that's the reason for calling it the simple harmonic oscillator. Okay, so where did this come from? Well, if you multiply both sides by m, you see it's Newton's second law. Mass times acceleration equaling the force, which is minus kx. The minus kx is the restoring force. in this one-dimensional problem. I want to say a few words about the notation. Again, we have used fairly streamlined notation. This x here you see, if you explicitly exhibit the argument, this is x as a function of time, that's a little bit cumbersome. So out of laziness, sometimes we just write x, but it's understood that this x is a function of time. K and m are constants, okay, but the x is a function of time. And this x double dot, of course, in physics, we love to use the dot to indicate a time derivative. This is the second time derivative, so that's d squared x dt squared. Sometimes people ask, why is it d squared x dt squared? Well, it's two applications of a differential operator. So you see it's ddt okay. So that's why when you see in the denominator, it's dt squared. You could put parentheses around the dt. We're not squaring the time itself, we're squaring dt. And that's clear if you look at this construction here. We have dt and we have dt, so that's the dt squared. Okay, this is certainly not okay. That crossed out equal sign indicates it's not equal to. Obviously, this is fundamentally different. You see the units are different. We have meters squared per second squared, and this is meters per second squared. So the units are different. This is the square of the velocity. Okay, just want to mention these things because sometimes students ask about that, and it's good to be very clear on the basics here. Again, we've suppressed the argument. This is a function of time. So if x is a function of time, then the time derivative, the first derivative, the second derivative, and higher derivative, they're all functions of time. Okay, great. So the question is, how do we solve this differential equation? We know, based on our recent musings, that since we do have a conserved quantity, right? We have a conserved quantity, so notice that the total energy so there's the kinetic. There's the potential. If you compute the time derivative, what happens? dE dt. Okay. This is called a conserved quantity, and this will be very important to us later in the course. We're actually going to talk about different spaces. Not only the physical space that we live in, which has x, y, and z axes. Each of those axes has dimensions of meters. We'll talk about other spaces like phase space, where some of the axes have dimensions of meters, some of the axes have kilogram meters per second momentum, right? And we'll be interested in functions on phase space. So this kinetic energy, you know, it can be written as the momentum squared over 2m, right? So this is a function on phase space, and the trajectory of the system through phase space moves along contours, okay? So those are some remarks for later in the course. We're going to appreciate the geometrical setting of objects like this. For the moment, let's simply compute the derivative. If you compute the time derivative of this object, of course, we'll use the chain rule here. We have x dot squared. So we differentiate. We have 2 canceling this 1/2. And then we have x dot, and the chain rule tells us we must compute the derivative of x dot. That's going to give us the x double dot. And then we'll plug in this. Over here, we have a constant times x squared. We differentiate. We have 2x times x dot. Okay. So again, if you plug in this, you see it's 0. Okay, so that's a wonderful state of affairs. And let me make a quick remark and then I'll address the chat window. This is a very special luxury if you have a conserved quantity. Thinking back to the diagram I displayed a moment ago, this allows us to use some special techniques and we could rapidly get the answer. We do not have to suffer through a long process of solving a differential equation. If you have a conserved quantity, you're in a much better situation. And we have For one-dimensional motion, we have a very clear prescription on how you can compute t as a function of x. And in principle, it's just functional inversion. Finding the inverse function, x as a function of t, is considered a trivial operation. And so that gives you the solution. All right, so we got a question in the chat window. Will we be using Laplace and or Fourier transforms for problems? Great question. In this course, we will not be using the Laplace or Fourier transforms, but you've made an excellent remark. Actually, I see this was a private question. So a student asked about the methods of Laplace transforms and or Fourier transforms. Yes, that's fascinating stuff. I would recommend Physics 89. That's a course where, and when I teach that course, I do cover that stuff. But again, we have to budget our time this summer, and the topics that you mentioned, using Laplace transforms and using Fourier transforms, fascinating stuff, but unfortunately, we won't have time for that this summer. Okay, so we're going to talk about how are you going to solve this differential equation in general. Suppose you didn't know about this conserved quantity. Or another way to say it is, looking ahead to what we're going to do next, we're going to include some more physics. We're going to include a mechanism for dissipation of mechanical energy, friction. Right? We're going to include a special model for friction. One thing that is cool about Taylor's book is he actually, in the earlier chapters, goes to great lengths to talk about friction, because real life systems do have friction. And often in mechanics courses, friction is viewed as kind of an unpleasant annoyance, and let's not talk about it. So what we're going to do is introduce a term where there's a frictional force proportional to the velocity. It turns out that's a little bit artificial. In actual practice, that's kind of a rare state of events. You can cook up some examples where it's somewhat proportional to velocity, but thinking back to the 7 sequence and the 5 sequence, when you talked about friction, you had static friction, you had kinetic friction. Remarkably, the kinetic friction was independent of the velocity. It only cared about the normal component, but then it did not care how quickly or slowly you were moving a box across a horizontal surface, for example. So that model for friction was proportional to velocity raised to the 0th power. Then other models for friction are proportional to velocity squared. What we're going to do is look at a model for friction where the frictional force is proportional to the velocity. It opposes the motion, so the direction of the frictional force is -1 times the direction of the velocity. So when we do that, then we will not have the luxury of having a conserved quantity. So it is for that reason that we want to introduce a technique for solving this differential equation, which will be robust enough that we can start adding terms. We're going to add another term with the friction, then we'll add another term with a driving force. So we'll keep adding more terms to this differential equation. Okay, so in general, we're going to look at the so-called exponential onsets. Okay, so let me organize the thinking. This stuff, that was really just a thought bubble. Those are some thoughts about x double dot. So now I'm going to resume the discussion here, the general solution. Okay, we attempt to solve this using an exponential onsets. Okay, so we'll have 2 complex coefficients, C1, and we'll have an e to the I omega t plus C2 okay. And here, this omega is defined to be the square root of k over m. All right, that's easy to remember. If you increase the mass, the whole thing becomes more sluggish, the frequency is reduced. If you increase the spring constants, they have a much stiffer spring, then the frequency is increased. So omega is this root k over m. Okay, so you can see by direct substitution, let me scoot this down like so. This term, e to the plus I omega t, is a solution because second order time differentiation is the same as 2 multiplications with I omega. That's minus omega squared. That's precisely this thing here. Okay. The same remarks are true about the second term. Second order time differentiation here gives you 2 multiplicative factors of minus I omega t. And the square of minus I omega, again, is minus omega squared. That's just what you see here as the prefactor. So these two terms are both solutions to the differential equation. Okay. Now, we have to organize the thinking in terms of these constants. We have 2 arbitrary constants. We observed that each of these 2 terms, I see there's there's a question in the chat window. I'll address that in just a moment. Each of these 2 terms is a solution to the differential equation. All right. And each one of them individually by themselves, since they're solutions, you can form arbitrary linear combinations. You could select C1 to be 0 and C2 to be some positive constant, for example, and you would have a solution. Okay, so the important thing right now is that there are 2 free parameters here, and this agrees with our experience from mechanics. The initial state, the classical state of the system, is defined by the position and velocity of the particle. If you know the position and velocity of the particle at some time, then the subsequent evolution, the time evolution of the system, is fully determined by that initial state. Okay, you can make remarks about quantum mechanics, right? You have a in quantum mechanics, you have a notion of the quantum mechanical state. That's completely different. Here in classical physics, if you know those 2 numbers, the position and the velocity, then the subsequent time evolution of the system is fully determined. Okay, and for that reason, we need to have these 2 free parameters. That's why this is the general solution. At some time that you choose, you can have t equals 0 or some positive or negative value t naught. If you know the position and the velocity at that time, then you can determine these 2 constants. Okay, and then you fully determine the solution. That's guaranteed then to be the unique solution. Okay, so now we had a question in the chat window, the significance of the signs. Okay, we have these 2 terms, the plus sign and the minus sign. All right, so that's a great question. There are times when we have similar looking formulas in the absence of this imaginary unit. Okay, we will see equations where there's a very similar structure, except there's no lowercase I here and there's no lowercase I here. Then the 2 terms are identified as exponentially growing and exponentially decaying. And yesterday in our first lecture, we talked about some wonderful work and some slides produced by Kathleen Howell. Remember, Kathleen Howell is professor at Purdue University. And this was a fascinating discussion of stable and unstable manifolds. Okay. Remember yesterday we surveyed the work of many researchers, Martin Lowe, Kathleen Howell, and Manuela, I'm not sure how to pronounce her last name, but starts with a V. And all of these researchers are doing fascinating things. So in the slides by Kathleen Howell, we talked about stable and unstable manifolds. Okay. In fact, what we did is we made introductory remarks, because to truly explain what stable and unstable manifolds are is going to require some effort. Later in the course, we'll talk some more about stable and unstable manifolds. And at that time, the plus and minus sign will be very important to us. Okay. We will have exponentially growing and exponentially decaying excursions away from equilibrium. And in chapter 12, we'll talk about chaos. And in the theory of chaos, you have these so-called Lyapunov exponents. And again, you have this notion of exponential growth. The butterfly effect, if you take the entire planet Earth, make a copy, except one little butterfly has the wings in a different position, and then evolve the system, you'll see that that tiny change grows exponentially because it's a chaotic system. And you check back later and the planet Earth is completely different just because that little butterfly had the wings in a different position. That's called the butterfly effect. Yeah, so we will be talking about cases where we have real exponents, and the plus and minus signs are important to us there for exponential growth and decay. Here, we simply are expressing the fact that there are 2 solutions. Really what's happening is you have this k over m, that's omega squared. And so there are two solutions, there are two square roots. So this is just a way of organizing the fact that we have two square roots. Two square roots, a positive square root and a negative square root. And we chose for concreteness to have this omega be positive. This notation indicates the positive square root. This is like if you have a calculator, if there's a square root button, it gives you the positive square root. It doesn't start arguing with you and saying, well, you know, there are really two roots. It just by convention, this is the positive root. Okay, so yeah, there are two roots, the positive and negative, and we've arbitrarily chosen this symbol omega to indicate the positive root. And so that's why we have to exhibit these two solutions like this with a plus omega and a minus omega. Okay, so this is one way to write it, but you know, we love to introduce other ways to write it. So you can use well-known identities that e to the I theta, right? Okay, we got the cosine theta. Okay, so this well-known result is going to be helpful here, but I feel we need a little comic relief. So I know there's a physics joke here. I'm trying to remember this physics joke. This will be a really funny physics joke if I can remember it. Okay, what I'm going to have to do here is I'm going to have to tell you the punchline. Yeah, it's oh yeah, here's how it goes. If you write it like this, e to the I pi. Let's see if I can do this. Yeah, the punchline is going to be that we have these two kind of forbidden things, the square root of a negative number and the logarithm of a negative number. Let's see if I can remember this. So e to the I pi equaling -1. Yeah, let's take the logarithm of both sides. And so we'll use this symbol ln for natural logarithm. So you have I pi equaling the natural logarithm of -1. Okay, so far so good. And so pi, you see pi is equal to right, you know, I is the square root of -1. Okay, there you have it. This is a little physics joke, right? You see that pi, this is pi, 3.14. Everybody loves this number, right? It's a real number, positive, wonderful. Pi is the ratio of two kind of forbidden things. The logarithm, that's the natural logarithm of -1, and that's the square root of -1. So isn't that funny? I think it's funny. Pi, this ubiquitous constant, is the ratio of the logarithm of -1 to the square root of -1. Okay, yeah, that was a little physics joke just to liven things up here. Let's return to the main plot. We're going to use this form here and rewrite. We have an alternative way to write this solution. So x of t we got the b1 cosine omega t. Okay, so this is fully equivalent, and let's really emphasize something here. In terms of solving the differential equation, remember we remarked you can have arbitrary complex coefficients C1 and C2. Arbitrary, and the same is true here. You could use complex coefficients B1 and B2. You could do that. But in practice, we're interested in real solutions. So at this point here, when we have this expression with the B1 and B2, here we declare that the coefficients B1 and B2 must be real. That ensures that you have a real solution for all time. Okay. Again, in terms of pure mathematics, you would allow, you could allow B1 and B2 to be complex. This would give you a complex solution to the differential equation. Okay. So what I want to do is make a few quick remarks about an example, right? We like to look for examples of simple harmonic motion. One example is, I'll display a picture. Maybe I should do this. Okay. Again, I'm going to do a little origami here. I'm doing some origami to avoid PowerPoint overload, okay? We don't want PowerPoint overload. We have enough things to worry about. Let's not get into PowerPoint. If I started displaying a lot of PowerPoint slides, right, the danger is PowerPoint overload. So let me just display this little picture. This is an example, right? This is example 5.2 from the text. It's a fun example in the sense that this is an experiment you could do, all right? In fact, next time you're at a party, if you see some beverages in a large container with water, you could do this experiment. Okay, what's happening here, this picture shows a container of water, and I've labeled the water. And here's this bottle, and what we've done is we put some ballast in there, some sand at the bottom, so that the bottle will float upright, okay? And then we introduce a coordinate to measure the position, okay, relative to the surface of the water, okay? You go through a little calculation. We'll skip the details. We're not concerned with these details right now. The point is there's an equilibrium when the bottle is motionless. Now, suppose you push down on the bottle slightly. You just take your finger, put it right here, and push down on the bottle slightly. You'll feel buoyancy. The buoyant force is pushing up against your finger, okay? Because you're displacing the system away from equilibrium. You've pushed the bottle down into the water slightly, and so that's an excursion away from equilibrium. If you release it, there'll be an oscillation, okay? And in Taylor's book, what he does is we look at a small excursion away from the equilibrium position, okay? What I just want to mention here is there's a certain dose of reality which sinks in here. If you do this experiment, I just want to caution you, the numbers are not going to work out so nicely, and here's why. Okay, let's draw a picture. Okay, you can go, so for me, it's a Berkeley Marine. I hope all of you around the world have access to water access, right? So I'm going to draw a picture of a boat. This is a side view. Here's a boat. Okay, again, that's a side view of the boat. And here's the water. I'll draw that in pencil. Okay, we got the boat, we got the water. Imagine it's one of those nice, peaceful mornings. You go down to the marina, the water's like a sheet of glass. It happens if it's not windy overnight, you can have very calm water in the morning. Okay, so here's this boat. And suppose you decide you're going to measure the mass of the boat by applying a small force and measuring the acceleration of the boat. It seems logical. You could determine the mass of the boat. You could use a rubber band, for example, to apply a very small force, tie the rubber band to the bow. There's a so-called bow painter. That's the line that attaches to the bow. Tie the rubber band there and just pull with 1 pound of force, for example. Measure the acceleration. The idea is you're moving the boat very slowly. You're hoping to do an experiment where you don't generate a lot of white water and turbulent water. Unfortunately, there's a certain reality that sets in here. No matter how slowly you do this experiment, you're going to get the wrong answer for the mass of the boat. Depending on the boat, you're going to be off by a factor of 2 or 3. It's not a small factor, it's a large factor, 2 or 3. And the reason is no matter how slowly you do this experiment, you must necessarily move some water. If you're going to move the boat a small distance, then it's necessarily true that the water has to move around. So again, no matter how slowly you do this, you must necessarily move some water. How much water depends on the exact shape of the hull of the boat. So it's a complicated, people in naval architecture, they know about this. It's a complicated story, but the same principles apply to this problem here. So the point is, when you read this example, it's a fun example. In principle, you could do the experiment, especially at a party, but I'm just trying to help you. All the people that you promise results to are going to get mad when it doesn't work out. And the reason it doesn't work out is even for small oscillations, the water necessarily must move. So here's an example where the quasi-static approximation is really not correct. What is the quasi-static approximation? Well, we looked at the equilibrium, then we considered a small excursion away from equilibrium, and then we waited for equilibrium to establish itself again. Then we could use Archimedes' principle to tell us about the buoyant force. Okay, so this is an example where we're doing a quasi-static approximation. We talk about various equilibrium positions. If you do that, then the answer is you have a simple harmonic oscillator. You go through the algebra, you look at this little excursion x, et cetera, and so forth. Right, so the answer is you create a problem which mathematically is a simple harmonic oscillator. The technical jargon for what you have done is a quasi-static approximation. Sometimes quasi-static approximations are pretty good. In this case, it won't work. No matter how slowly you do this, no matter how small the amplitude is, you're going to get the wrong answer for the frequency. And it will not, your audience is not going to be happy. You're trying to explain why you're off by a factor of 2, even though you've carefully measured all this stuff. Okay, so that is a nice little example of, I mean, the purpose of example 5.2 is to look for an interesting real-world example of a simple harmonic oscillator. This idea that simple harmonic oscillators are all around us. If you want precision results, you'd be much better off looking at a pendulum. Here I'm mimicking a pendulum. And I see there's a 180-degree phase shift between my zoom display and pencil. That tells me about the time lag. Okay. So, yep, that was a nice illustration of simple harmonic oscillator and some cautionary remarks about quasi-static approximations. Okay, so what we do next is we introduce a viscous force. All right, and the important thing to notice here is we assume a very special force. So the damped harmonic oscillator. Okay, so we're going to assume that we have a viscous force. So as a subscript, I admit I wrote it pretty small, it's viscous. And we're going to assume this is a negative constant times the velocity. So minus b times v. Okay, the minus sign sure makes sense. This force should point in the opposite direction. If the velocity is positive, for example, then this force should oppose it and point in the negative direction. Okay, so our differential equation, it's very nice to write the differential equation like this. Okay, you see we're going to bring this to the left-hand side. Okay, I see my document camera. Let's do this. I'm trying to optimize my document camera. That's pretty good. All right, so mx double dot, we got and we've got a kx. Okay, so you see where this came from. It's good old mass times acceleration equals the force. If you place these two terms on the right-hand side, they both get minus signs, and you recognize the familiar Hooke's law and this viscous force that we've just introduced. Okay, so what we're going to do now is observe that you can once again do an exponential Onsets. All right, we're going to skip the details because, again, much of this was covered in Physics 7a and Physics 5a. All right, let's consider solutions of the form. We should have some sort of multiplicative constant. In the text, this gets left out, but for the units to work out, you do need to have a constant here times e to the RT. Okay, And you can see something wonderful is going to happen here. We've taken a differential equation. In general, differential equations are very difficult to solve. But with this ansatz, we have reduced the problem to solving a quadratic equation. That's just an algebra problem. Okay, so we plug it in. You see second order time differentiation brings out two multiplicative factors of r. We get a quadratic equation. Okay, and we get these two solutions. And we use this very popular notation R1, 2. That is to say, out of laziness, we don't want to write the two solutions separately. So out of laziness, we're going to put the two solutions into a single formula, minus beta plus or minus okay, we have these two constants, the omega naught. This is the value of omega if there were no dissipation. If this viscous term were absent, then this would be the fundamental frequency. So it's natural to call this omega naught. This would be the omega in the absence of any dissipation. It's also helpful to define beta. These are simply definitions of helpful quantities. Beta is that little b that we introduced over 2m. Okay, and the same thing applies to exams. If you're taking an exam, you can do this. You can define whatever symbol you like to help in the sense that you don't have to copy, right? We don't want to write b over 2m. You don't want to write that 1,000 times. It's cumbersome. So just introduce a symbol. In this case, that's beta. That's a lowercase Greek beta. Okay. So here we have our two solutions. And now we can write down the general solution. Okay, we got our C1 e to the R1t. Okay, so you see, okay, we have a, what are the units of B? Okay, great question, and we have a proposed answer inverse time. Let's look at our B. Well, you see each of these terms, let me pull this down here. Each of these terms has dimension of a force, right? And you can see that here. So yeah, this B is going to be force over velocity. So force is measured in newtons. That's kilogram meters per second squared, right? Those are the dimensions of a force. And then velocity, so we're taking that, and the dimension of velocity, meters per second. Okay, so now we need to clean up a little bit. We got a cancellation, and it looks like kilograms per second. Let's see. So I believe this B is kilograms per second. And then you see beta would be inverse seconds. So these are marks, maybe I should use a different color. This is a remark for the units, and all these are remarks. So I've used this red color to indicate we have some, that's a great question. You should always think about units. So yeah, something wonderful happens here. Omega naught, certainly inverse seconds. And now beta, of course, also with inverse seconds. So it works out very nicely. Yep, that's a great idea to check the units. Okay, so what happens now is there's some bookkeeping to be done, right? We have several cases, the overdamped, the underdamped, right? Beta greater than omega naught, beta less than omega naught, and beta equal to omega naught. So we're being very pedantic here And then we're rewarded. This is a special case when beta is equal to beta and omega naught. There's something special that happens. Okay, how did we arrive? There's a question in the chat window. How did we arrive at the equation for beta? Okay, so this this equation here was just for convenience. All right, we saw the occurrence of the b over 2m. So here, this is a definition for convenience. Okay, so in answer to the question that I have in the chat window, this was for convenience because when you write down the quadratic equation, there's a certain factor of 2, which is annoying. We want to remove any sort of annoyances and just have some smooth sailing. And so, yeah, the ansatz really, that's just a fancy term for an educated guess. It is justified once you plug in and show that your ansatz is successful. If you can successfully solve the differential equation, and if you have the 2 free parameters, then you have found the solution. We'll say some special words about this last case in our next meeting. Okay, so that brings us to the end of the hour. I will pause the recording, and I will stay here for a little while and see if you have any questions.